Hi class, welcome again. Today's lesson, we are going to learn on the effect of internal resistance on the terminal potential difference. This is Puan Anita teaching for Physics Form 6 Sem 2. The learning outcome for today is to explain the effect of internal resistance on the terminal potential difference of a battery in a circuit. Before we look at internal resistance, let's understand a little bit about electromotive force, EMF. Let's look at your Oxford FAJAR reference book, and in page 98, let's look at what is the important concept that we can actually absorb from this page 98. Okay, the book says in point number 1, the electric circuit requires a source of electromotive force to drive current around the circuit. Okay, now what is electromotive force, class? Now, electromotive force is not a force at all. Okay, so if the electromotive force is not a force at all, then what is EMF and what is the source of EMF? Okay, now let's look at here. Okay, now to answer this question, we consider a very simple circuit where we have a 12-volt battery, okay, connected to a lamp, which is also a 12-volt lamp. Alright, they are attached together. Alright, the battery can be modeled as a two-terminal device that keeps one terminal at a higher electric potential, and usually we will label it as a positive potential. And then here we have a lower electric potential, which is the negative terminal. Okay, the higher electric potential is also sometimes called as the positive terminal, and it's always labeled with the plus sign. The lower potential terminal is sometimes called as the negative terminal and is always labeled with the negative sign. So this is the source of EMF. Okay, alright, so when the EMF source is not connected to the lamp, okay, if this EMF source is not connected to the lamp, it's just a battery by itself, that means there is no net flow of charge within the EMF source. So no net flow of charge. Okay, alright, so in that case, if I take the battery, okay, I take the battery, I connect it to the lamp, but it is a circuit where if I put the switch, it's an open circuit. We call the word as open circuit. Then what happens, class? The EMF of a source, which is the E, the EMF of the source, which is the E, is the potential difference across the terminal of the source in open circuit. So that's what the book says in the second statement. The EMF of a source is the potential difference across the terminal of the source in open circuit. That is when no current flows from the source. Point number 2. So in this case, if you look at my diagram, if there is an open circuit, means the switch is open. When the switch is open, that means no current flow. When the no current flow, then it says the potential difference across the terminal of the source is what is the EMF of a source. Okay, so here it also says here in point number 3, the EMF of a source is defined. Okay, this is the definition of the EMF of a source. Okay, is defined as the energy supplied. Now here you have to look at two keywords here, right? So I'm going to put this particular keyword, supplied. Okay, energy supplied to each column of charge that flows from the source. Okay, so if I have a battery, which is the source, alright, so here we can talk between two charge. We want to talk a positive charge, then we'll talk about from the positive terminal to the negative terminal. But if you want to talk about the negative charge, we talk from the negative terminal to the positive terminal. But here I'm just going to say the word charge as I'm explaining here. So I'm going to just take from this direction to this direction. So I'm going to emphasize on the positive charge. So the energy supplied to each column of charge that flows from the source. So this is the EMF. EMF is the energy supplied to each column of charge. Okay, energy supplied to each column of charge. So you see, they use the word here is supplied because energy has to be supplied to the charge, okay, which is in the battery. Okay, so each column of charge that flows from the source. Okay, so if you have a lamp here, is that so? Understand or not? Alright, so EMF of the source is defined as energy supply to each column of charge. So we can say EMF is E over Q. E over Q, where E is energy supplied. Okay, now it is measured in joule per coulomb because E is joule, Q is coulomb, which is equivalent to watt. Alright, which is equivalent to watt, the unit for EMF. Either it can be joule per coulomb, unit for EMF joule per coulomb, or watt. Okay, alternatively, the book says alternatively. Okay, there is another way of defining the EMF. Now, how do you define the EMF? We look at that particular keyword, which is dissipated. So, when it talks about dissipated, that means it's somewhere around the circuit. Okay, that means some energy is lost. So, what does the book say? Total energy dissipated in the circuit divided by charge that flows around the circuit. Okay, when we talk about the battery, referring to the definition towards the battery, we use the word energy supply. But when we talk about around the circuit, then we use the word dissipated. Okay, so from here, we can say that the EMF is E over Q. Okay, and then we know that power is E over T. Correct? Alright, so we substitute inside this formula, we get PT over Q. And then we also know is Q is equals to IT. Okay, so 1 over I is equals to T over Q. So this thing here, T over Q is 1 over I. So I get P over I. Okay, which is then gives you to the alternatively the second definition. Total power dissipated in the circuit current in the circuit. Okay, so either you want to define it in the sense of energy or in the understanding of power. Okay, so this is a definition of supply. This is the definition of lost energy in the circuit. Okay, now let's look at an example here. The EMF of a dry cell is 1.5 volt. Okay, now I have a dry cell. The EMF is 1.5 volt. Means that, okay, every 1 coulomb of charge that flows from the cell. So if there is a charge of 1 coulomb of charge, again I say I am referring to positive charge. If I'm talking about negative charge, then I will be talking about the opposite direction. Okay, so here is I give 1.5 volt of EMF here means that every 1 coulomb of charge that flows from the cell is provided with 1.5 joule of energy. Okay, that means what, class? Alright, let me take another color pen here. That means from 1 coulomb of charge, supply energy is how much? Is 1.5 joule of energy. Okay, 1.5 joule of energy. In the same manner, we can also say the energy of 1.5 joule is completely dissipated when one coulomb of charge goes around the complete circuit. That means if the charge goes around the complete circuit, what will happen if I have a lamp here is 1.5 joule of energy. Okay, completely dissipated when one coulomb of charge goes through here. So there are two ways of explaining the EMF. One is supply, one is dissipated, the definition. Okay, now let's look at point number 6. The book says a quick but inaccurate method of measuring the EMF of a source is to connect a high resistance voltmeter across the cell. Alright, so this we know, class. Okay, now this is of course inaccurate method is to use a voltmeter, high resistance voltmeter. So we know V is equals to IR. Okay, so if resistance is high, so current will be very low. So that's why they say current is negligible. Okay, the current that flows in the voltmeter is negligible. So which is the next sentence. Since the resistance of the voltmeter is high, then the current flow from the cell is negligible. Hence, the reading of the voltmeter gives the EMF of the cell. Okay, so I have a EMF. This is an EMF. Okay, this is not a complete circuit. Okay, so we consider this as an open circuit. So when an open circuit, if I connect this to a voltmeter, okay, so there is no current that flows in the voltmeter. It's considered negligible. Alright, and it's a very high resistance. Take note of that, high resistance. Okay, so what will the voltmeter gives the reading? The voltmeter will give the reading of the EMF. Okay, either EMF or we put small e, small m, small f, EMF. Alright, so that's what it's trying to say. A source of EMF has internal resistance. Okay, a source of EMF has internal resistance. Now, the internal resistance of a dry cell is due to the resistance of the chemical in the cell. That means inside an EMF, we have a internal resistance which is small r. Okay, the internal resistance will affect the reading if there is a current flow in the circuit. Okay, so in other words, I can say is the resistance within a battery is called the internal resistance. Okay, alright, the internal resistance causes a drop in the battery voltage when there is a current flowing. Okay, so if this is a closed circuit, if I have a lamp here, this is called as a closed circuit. This internal resistance will affect the voltage of the battery when there is a flow of current. Okay, alright, so that's what they're trying to say here in point number 6, point number 7. Okay, now the internal resistance of an electric generator is the resistance of the wire used for the coil. Okay, this one all is just a reading thing for you all to know. Okay, the internal resistance of a source constitute part of the total resistance in the circuit. That means when you want to calculate the total resistance in the circuit, the internal resistance will affect. That means it's a part. Okay, it constitutes part. That means it's a part of the total resistance in the circuit. So you have to include it when you include the total resistance in the circuit. That's what it's trying to say. Okay, now the maximum current that can flow from the source is determined by the internal resistance of the source. So that means if the EMF has an internal resistance, the maximum current that flows out will be what? Will be determined by the value of your internal resistance of the source. Okay, so that's what they're trying to say. Okay, so what is the main important concept in this page, class? We have to know the definition of EMF. Okay, And then we have to know in an open circuit, we have a EMF here. Okay, either in an open circuit like this, with the switch is open, or we have like this, just a single cell connected to a voltmeter. The voltmeter will give the reading of the EMF. Okay, and then we know that internal resistance will affect, internal resistance in the EMF will affect and cause a drop in the battery voltage when there is a current flowing. Right? Okay, so that is for this internal resistance.
And now let's understand how an internal resistance in a cell can affect on the terminal potential difference in a circuit.
On the effect of internal resistance on the terminal of potential difference. Okay, terminal potential difference are referring to VT. How does internal resistance of the battery will affect the terminal potential difference? So before we go to the main concept, just let's look at certain facts here one by one. The potential difference, okay, V, between 2 points in a circuit. Okay, we have 2 points in a circuit, that means external circuit. Yeah, so we have maybe a resistance here, is defined as the ratio of energy dissipated between the 2 points to the charge that flows. Okay, so this is potential difference, is energy dissipated over charge. Okay, energy dissipated over charge is still the same formula, E over Q. EMF is supply, okay, and potential difference is energy dissipated over charge. The unit for potential difference is volt. Okay, the same way as I explained to you, you can also say in the word of power and current. Okay, power over current. Okay, here is EMF, but this one is potential difference. EMF is of the battery, potential difference is the voltage difference between 2 points in a circuit. Okay, alright, so now let's look at this next sentence. From potential difference, V equals to power over current. So we have this formula. Okay, what they are trying to say, class, you see, class, when we are talking about power over current, okay, when we have a battery connected to a lamp, the power will be the power supply, which is IV. When we talk about power dissipated, we have to use two formulas, which is power is equals to I square R, or power is equals to V square over R. So that's how they get the formula here. Okay, actually both of this formula is from the main formula, which is P equals to VI. Okay, alright, so now I'm going to look at the main concept here in this page, the effect of internal resistance on the terminal potential difference. Okay, now we have a battery which is connected to a lamp. Okay, now we have here a switch. Now terminal potential difference, VT, okay, is the potential difference across the battery. That means it's the potential difference from this point to this point across the battery. Okay, if a battery has no internal resistance, that means no resistance, internal resistance, and supply a current to an external resistor, okay, we in this lamp got resistance, then the terminal potential difference is equals to the electromotive force if the circuit is closed. Okay, but if the battery has an internal resistance, right, and supply a current to an external resistor, there's a current flow, then the terminal potential difference VT will be less than the electromotive force EMF E of the battery by amount that is equals to IR. Okay, so now go back to what we have studied before this. Okay, alright, let's look at this. I have a battery, I have a resistor, and here is switch is open. if I connect this to a voltmeter, the voltmeter will give the reading of EMF E. Even though there's an internal resistance, because the switch is open, this is an open circuit, no current flow. When no current flow, voltmeter gives the reading of EMF. Okay, alright. Next, the second situation is, if I have a battery and it's a closed circuit. Okay, so when this one we have E, this one we have R, current will start to flow. When the current will start to flow, the voltage terminal, which is the voltage from this point to this point across the battery, Vt will be less than the EMF. Okay, why? Because there is a voltage drop inside the battery due to the internal resistance. So E is equals to Vt plus Vd. Okay, E is equals to what? Vt plus Vd. So if I take E minus Vt, I will get Vd. So E minus Vt is equals to I times R. So the difference of the voltage drop will be IR. Okay, alright. Alright, so that is what they're trying to say. And if I want to fix this to a voltmeter, the voltmeter will give the reading of Vt. Okay, voltage terminal. So that's what they're trying to say. So what is the effect of internal resistance on the potential difference? The effect of internal resistance on the potential difference will be, it will give a value less than the value of EMF. Okay, alright, so that's why you see in your textbook in this page here, due to the internal resistance, the potential difference across the terminal, which is actually referring to Vt, of a cell in a closed circuit is less than the EMF of the cell. That means E is less than, Vt is less than the EMF of a cell. This is the effect of internal resistance on the terminal of potential difference. Okay, so this is because energy is required to drive the electric charge through the material of the cell. So we get E is equals to Vt plus Vd. Okay, so E minus Vt is equals to Vd. E minus Vt is equals to IR. So how much it is less is by IR. Okay, so that is the concept. Okay, now let's look at the next page. We have an example here, which is figure 15.2. Now here we have a resistor, a variable resistor here, and then here we have an EMF with the internal resistance R, and then here we have an ammeter to measure the current that flows in the circuit, and then we also have a voltmeter here to measure the voltage between this point to this point. Okay, so the reading the reading V and I of the voltmeter and ammeter are recorded for different values. So we have V over I. Okay, so we have V over I. So what can we say here is, okay, we know the basic concept, E is equals to Vt plus Vd. Okay, and E is also equals to Vt plus IR. Okay, and then I bring Vt here. Vt is equals to E minus IR. That means Vt E minus IR. I bring it to the other side. So E minus IR. Then I compare with Y equals to Mx plus C. So E is the potential. E is C, y-intercept, and then you can compare here. X is I, Y is Vt, x is I, and then y-intercept is E. So therefore, what is that? Therefore, the gradient of the graph represent to negative R. M is equals to negative R. That's why you get your gradient of the graph is negative R. Okay, so this is how to understand it in the form of a graph. Alright, so from this, okay, they get the internal resistance. Gradient of the straight line is negative R. Okay, and then they also do the same way here. This formula, which I've already taught you before. Okay, how do you do that? Okay, how do you do that? Wait, let me see. Okay. E is equals to Vt plus Vd. Okay, Vt is IR plus Vd is I small r divided by I capital R divided by I capital R divided by I capital R. So I get 1 plus R over R. Here I convert back to Vt, so I get the formula as the book has mentioned. Okay, so I get this formula here. Okay, and then they said if they do another experiment where they plot the graph of 1 over V equals to 1 over R, they notice that the gradient of the graph is R, internal resistance. In the same manner, you also do the one that is equivalent like this now what we did. Okay, so hence the internal resistance of the cell is the R is equals to the gradient of the straight line. Okay, alright, so here if you see in point number 12, okay, point number 12, okay, what do you see, class? Now this is the same concept as a resistant. We have 3 cell, alright, we have 3 cell here, cell number 1, cell number 2, cell number 3. So if you want to find effective EMF, we plus all 3 together because they are in series. So we take E plus E plus E is 3E. Okay, now why is it like that? It is the similar as the one that which you have it in resistance. Okay, and then the concept which you have resistance in series. Yeah, that's the right word. Okay, effective internal resistance also will be the same. You take R plus R plus R, you get 3R. Okay, same goes to a parallel cell that is arranged in parallel. Okay, so the concept is the same as the resistor that is arranged in parallel. So what do you do in this 3 case? Effective EMF will be E. Okay, effective resistance will be so 1 over R plus 1 over R plus 1 over R. So 1 over R effective will be like this. It's same concept as resistor in series and parallel. Series and parallel, same way. Only thing different is here we are talking about more cells and more internal resistance. Okay, but the one that you solve resistor in series and parallel, you're talking about across the circuit. This one we're talking about 3 cells together, or 3 cells that is arranged in parallel. Okay, so next one, maximum power. Okay, maximum power happens. Okay, now let's look at this diagram here in figure 15.7. Okay, it says here when a cell of EMF E and internal resistance R is connected to an external resistor, the power dissipated from the external resistor is maximum. Okay, this one is important keyword. The power dissipated from the external resistor is maximum when the resistance of the external resistor equal the internal resistance of the cell. That means if this R and this R is same value, then the power dissipated from the external resistor P. External resistor power dissipated from the external resistor is maximum. So this is one concept you should know. If the R is the same as this small r, the same value, so the power dissipated from the external resistor is maximum. So this is an important keyword. Okay, then they prove how does it go so, and then here they managed to prove it that the power dissipated from the resistor of resistance R is maximum when R is equals to small r. Okay, all right, so that's all class, and thank you class.